Welcome to Crisis in Perception, where we examine the systems shaping our world one book at a time. Today, we are embarking on a truly fundamental deep dive, and we're moving past the systems of power or economics, and we're really grappling with the systems that define reality itself.
We are. And our guide for this is Brian Cox and Jeff Forshaw's essential work, Why Does E equals MC? And Why Should We Care?
And this is so much more than just a pop-sci book about physics, isn't it? It's an intellectual journey that really forces you to question the very basis of your everyday observations.
It does. I think our core systemic question today is this. Why did humanity, after thousands of years of success, relying on common sense intuition, the intuition that was formalized by Newton, why did we have to abandon it completely?
And not just abandon it, but abandon it in favor of this.
Yeah.
This abstract mathematical structure.
Exactly. And how specifically did that radical, almost painful conceptual shift lead us directly to the equivalence of mass and energy?
That's the crisis in perception right there. I mean, we are built to believe that the space we occupy and the time we measure are fixed, universal constants.
The stage.
Yeah, the absolute unchanging stage upon which everything unfolds. Our senses, our entire experience tells us this has to be true.
But it's not.
And the frameworks, the critical technologies that literally shape our daily lives, I'm talking about GPS navigating your drive, the light from distant stars, they all rely on principles that fundamentally contradict that basic ingrained perception.
It's the ultimate paradox of modern knowledge.
Yeah.
What works for us here on Earth, dealing with cars and falling apples, it utterly fails at the edges of the universe.
Whether you're looking at things moving near the speed of light or at the tiniest quantum scales.
Right. So our mission today is to explicitly examine physics not as just a set of rules or formulas, but as a rigid, conceptual, and mathematical system.
A structure.
A highly consistent structure of relationships and symmetries that simply cannot tolerate contradiction. We're built to be intuitive, big world mechanics, but the universe, it just insists that its deepest truths are fundamentally counterintuitive.
So let's look at the guides taking us through this really challenging territory. Brian Cox and Jeff Forshaw.
They're both celebrated physicists from Manchester, and maybe more importantly, they are masters of communication.
And their objective in this book isn't to mystify you, right? It's the opposite. It's to demystify.
Exactly. They approach this incredibly daunting equation, mc², with a promise. They say they will show you exactly how Einstein derived it, using only mathematical tools you likely already have.
Like Pythagoras' theorem.
Like Pythagoras' theorem. And what's really valuable about their approach for us as systems analysts is that they're revealing how modern physicists construct theories.
It's the process.
It is. The step-by-step process of demanding consistency from observations and then just following the mathematical consequences, even when those consequences seem completely insane.
And this is the process that builds these profoundly useful theories that govern, well, everything. How our stars shine, how an electric motor works.
How particle accelerators function. It's all the same system of thought.
So to really understand the scale of Einstein's revolution, we have to acknowledge the historical system collapse he walked into.
We do. For millennia, starting with Aristotle and then formalized magnificently by Galileo and Sir Isaac Newton, the system of classical mechanics reigned supreme.
And the core assumption was what?
The conceptual assumption was that space and time were absolute and separate. Newton's laws of motion and gravitation were perfect. They predicted planetary movements, cannonball trajectories, the tides.
They stood completely unchallenged for over 2 centuries, right up until the early 1900s.
And then that system developed these deep, irreconcilable cracks in the late 19th century. And the problem didn't start in the stars. It started with benchtop experiments.
Right, with people like Michael Faraday.
Meticulous work with magnets and coils, leading to generators and motors. His physical observations were then translated by James Clerk Maxwell into a set of 4 just beautiful, elegant equations.
And those synthesized electricity and magnetism into a single thing, electromagnetism.
Yes. And those equations, which mathematically described how an electric field changing over time creates a magnetic field, and vice versa, they created an existential crisis for the whole Newtonian worldview.
Okay, why? What was the crisis?
Because Maxwell's equations, derived purely from this demand for mathematical consistency, predicted that electromagnetic waves must travel at a single fixed speed, a speed we call the tree.
And this speed was calculated directly from electrical and magnetic constants.
Yes, it didn't matter if the light source was moving toward you or away from you, it was always the same speed. And this just defied the fundamental Newtonian rule that all velocities are relative and additive.
Right, the classic example. If I throw a ball forward on a moving train, its speed relative to the ground is the speed of the train plus the speed of the ball.
But Maxwell's math said light doesn't work that way. It's always Diesler.
So the entire system of physics was split. You had a perfect system for motion, Newtonian mechanics, and a perfect system for light and electricity, Maxwell's electromagnetism.
And they fundamentally disagreed about how speed works.
A total contradiction.
Precisely. This is where the book delivers its core message so clearly and simply. The only way to resolve that contradiction is to realize that mass and energy are not separate, immutable substances.
They're interchangeable.
They are interchangeable expressions of a deeper, unified physical structure governed by the geometry and symmetry of what we now call space-time.
So if you take just one thing away from this deep dive, it should be this. Way EC22 is not some mystical formula for destruction. It is a fundamental statement about existence.
That's it. It's the exchange rate.
The exchange rate between the currency of energy, E, and the currency of mass.
M. They're the same underlying stuff, just expressed differently. And the conversion rate is the speed of light squared, 232.
And since C is enormous, 300 million meters per second C squared is just a staggeringly large number. 90 quadrillion.
And this immense conversion factor is why converting even a tiny, almost immeasurable amount of mass yields a truly phenomenal amount of energy.
The physical consequence is profound.
It is. Matter is simply locked up energy.
Okay, let's move into the rigorous analysis. We have to look at the conceptual leaps required to build the theory of relativity. And we can start with the very idea of standing still.
Right. So the foundational conceptual assumption we inherited from Aristotle and that Newton formalized was the existence of absolute space and absolute motion.
The belief that there has to be some kind of fixed universal grid.
A cosmic reference frame, yeah, relative to which we can determine if something is truly, truly at rest.
And that idea makes perfect sense for survival. You know, if you're hunting a woolly mammoth, you need to know where it is relative to the ground you're standing on. Our brains are hardwired for a fixed reference frame.
Of course. But the analysis, using the book's airplane example, just reveals the flaw.
Walk us through that.
Okay, so if you walk from the front of an airplane to the back, an observer inside the plane sees you move, what, maybe 20 meters? But an observer on the ground sees you move that 20 meters plus the hundreds of miles the plane has traveled over that same time. So who's right? Who is right about your trajectory and the distance you traveled?
Historically, Aristotle got this dead wrong, right? He assumed the Earth was the absolute fixed frame.
He did. Galileo's profound, crucial first step, which Einstein later extended, was realizing that the only thing that makes any sense is relative motion.
There's no experiment you can do, even in principle, that can detect absolute motion through space.
None. If you're sealed in a windowless room, you cannot tell if you are standing still or moving uniformly at 100,000 miles per hour. So the physical consequence of this is radical. Absolute space is a redundant, unobservable concept.
Okay, but if we abandon absolute space, the consequences are enormous. I mean, I'm holding this pen and I measure it to be 10 centimeters long. If you, in a spaceship whizzing past me at half the speed of light, measured it, you would insist it was shorter.
I would.
That throws away millennia of human expectation that physical objects have fixed dimensions.
It does. And that sets the stage for what we call length contraction, this idea that distance itself is subjective and dependent on relative motion. But to truly build a new system, we also have to sacrifice absolute time.
Which is even harder to accept.
Much harder. The conceptual assumption of the 19th century, which was designed to reconcile Newton with Maxwell, was the existence of something called the luminiferous ether.
The ether.
Yeah. The idea was, just as sound waves require air to travel through, light waves were assumed to require this invisible, pervasive medium.
And the speed of light, see, was fixed relative to that medium.
That was the idea. So if the Earth was moving through this ether, we should be able to detect an ether wind.
So if we measure the speed of light traveling in the same direction as the Earth's movement, it should seem slower. And if we measure it traveling perpendicular, it should seem faster. Is that right?
That's precisely what Albert Michelson and Edward Morley set out to detect in their famous experiments in the late 1880s.
And they used an interferometer, a fantastically precise instrument, to measure this.
They did. They measured the speed of light in different directions and at different times of the year as the Earth orbited the sun, changing its velocity through this assumed ether.
And what was the result?
A magnificent, terrifying failure.
Nothing.
They found absolutely no difference. The speed of light was always the same, regardless of the Earth's motion. This was a direct experimental refutation of the core Newtonian concept of velocity addition when you apply it to light. This was the system collapse.
It's incredible to think that physicists were actively avoiding the simplest conclusion,
Which was?
that the speed of light truly is constant for all observers. They tried to invent these complicated ways the ether might be dragged by the Earth, or ways the experimental apparatus might be flawed.
Of course they did, because accepting the constant speed of light, which became Einstein's first axiom, meant throwing away the most stable, most successful system of physics ever devised.
But Einstein just took it as bedrock.
He took the constancy of tellura, derived mathematically by Maxwell and confirmed empirically by Michelson and Morley, as the starting point. And the physical consequence of that is that the speed of light is constant for all observers, and this destroys the notion of absolute time.
Time and space themselves have to warp to protect the constancy of c.
That's it. They must.
So if space and time are subjective, if my clock ticks differently than yours, how do we have universal laws of physics? How do we rebuild the system?
We have to find something that is universal, something that all observers, regardless of their motion, can agree upon.
An invariant?
An invariant. The old conceptual assumption was that space, or distance, delta built, and time, or duration, delta tuatil, are independent. Einstein's system, which was formalized by his former professor Hermann Minkowski, demanded that the laws of physics must adhere to invariance and causality.
And to get that invariance, you have to unify space and time into a single entity.
Space-time.
Space-time.
Yes. Think of it like this. If I rotate this pen in 3D space, its length remains the same. It's invariant, even though its x, y, and z coordinates change for you. Space-time requires the same idea. The distance between two events in space-time must be invariant for all observers, even though their individual measurements of space, delta TL R2, will differ wildly.
But space and time are measured in different units, meters, and seconds. How do you, add apples and oranges?
You convert them. You use the only universal constant available, the speed of light, c dollars. We measure time in the currency of distance by multiplying it by c, so time becomes delta del TTA.
Okay.
Now, to find the invariant spacetime distance, which we call ZIL-dr, we need a geometry to combine them. The classical conceptual assumption would be to just use the standard Pythagorean theorem.
Right. C tall dollars equals CO, delta by C tool plus delta by 2, the geometry we use every day to find the length of a diagonal line.
But that geometry fails in relativity. It would allow an observer to rotate their perspective fast enough to find a frame where the time between two events flips.
Which violates causality. Cause has to precede effect.
Always. So the mathematical structure required to preserve causality is a non-Euclidean geometry, specifically hyperbolic space, which is defined by the Minkowski formula. And it's almost the same, but with one crucial difference.
What's the formula?
It's $2 equals c delta t2, delta by 2.
That single crucial minus sign.
That's it.
That's where all the weirdness of relativity comes from, isn't it?
It is the hinge of the entire system. It tells us that time and space are not merely interchangeable, like they are in Euclidean geometry. They are fundamentally distinct aspects of the same reality, and one of them has to be subtracted from the other to calculate the invariant distance.
So why does that minus sign enforce the cosmic speed limit?
Because if an object travels faster than a polar, the space term, delta by 2, becomes larger than the time term, co-c delta 2.
Which would make C2 negative.
Exactly. And the square root of a negative number is an imaginary number. In the physical system governed by this geometry, the square of the distance between two causally connected events has to be 0 or positive.
So the system structurally forbids motion where space is traversed faster than time allows?
That's it. This structure imposes the limit. If you plot this on a space-time diagram, you get what's called the light cone. Anything that happens outside your light cone, any event so far away in space or so close in time that information would have to travel faster than c to reach you, it simply cannot influence you.
So the geometry of space-time prevents paradoxes, like traveling backward in time.
It does. It isn't just the speed of light. It is the fundamental constant defining the structure of reality. And light respects it because photons, being massless, are forced to travel along the paths where that space-time interval, $2 total dollars, is exactly 0.
Okay, so now we take that warped four-dimensional structure of space-time and apply it to our concepts of mass and energy.
Yes.
Classically, momentum, PMBM, and energy were distinct, separate, conserved quantities.
But once you live in 4D space-time, you have to unify them. Just as space and time were unified into the space-time vector, momentum and energy must be unified into a single 4D quantity.
The energy-momentum 4 vector.
That's it.
This sounds incredibly abstract. Can you give us an analogy for a four-vector for the listener?
Sure. Think of it like this. Imagine a box sitting on a table, a 3D object. You and I might measure its length, width, and height differently depending on how we orient our measuring tapes.
Okay.
But the box itself, the object, is invariant. The four-vector is like that box. It's a single fundamental object in 4D spacetime. Three of its components are the spatial momentum, PR, and the fourth component, the time component, is the energy, $1.
So the goal is to make sure that the entire four-vector, the combined quantity of energy and momentum, is universally conserved and invariant for all observers.
Precisely. And the key mathematical structure is that this four-vector must have a fixed invariant length. And when you calculate the length of that vector, using the Minkowski geometry, with that critical minus sign again, the fixed length of the four-vector turns out to be mc².
And $1 is the mass.
The value of $1 is the only thing all observers agree on. The mass of the object when it is at rest. It's the rest mass.
That's the link. So if we look at an object standing still, its momentum p is 0.
Right. It's four vector points entirely along the time axis.
Yeah.
And in this specific rest frame, the time component of the four vector is the total energy of the object.
And by demanding that the length of this vector be invariant,
When you analyze that energy component, you are mathematically forced to the relationship required.
that gamma is the Lorentz factor that
Yeah.
describes the dilation of time and contraction of length at high speeds.
This is the moment of genesis for the world's most famous equation. But we use that equation, the mc², for objects that are standing still, like in a nuclear reactor. Exactly. For objects standing still, that gamma factor is just 1, so you get mc². But what's even more illuminating is the low-speed approximation.
Mm-hmm.
If you expand the full formula for small speeds, the speeds we encounter every single day, it simplifies into Celoprox mc² plus fracto mv².
That is beautiful. The total energy of a slow-moving object is exactly what classical physics demanded. The kinetic energy, a half mv² plus this massive new term, mc².
Which is the energy that exists even when the object is motionless.
The rest energy.
This rest energy, mc², reveals that mass is not an immutable substance, but a vast reservoir of stored energy. The physical consequence is that mass and energy are interchangeable manifestations of the same deeper physical quantity. Conservation of the four-vector is the overarching principle.
So you can convert the mass component into kinetic energy, but the total length of the vector stays the same.
It always stays the same.
I find the mundane examples of this principle so fascinating. A hot cup of coffee is slightly more massive than a cold cup of coffee.
It is, because the kinetic energy of its molecules, the heat, contributes to its total mass. A charged cell phone battery weighs slightly more than a dead one because the stored electrical energy has mass.
The change is immeasurably small, but the principle is absolute.
It is. The heat in that coffee cup, the energy holding the nucleus together, it all contributes to the total mass of the system, and it's all governed by that massive T-2 exchange rate.
Okay, so now we transition from the geometry of space-time, which is relativity, to the structure of matter and forces, which is quantum theory.
And the underlying system shifts its focus from invariance to symmetry. We're now dealing with the standard model built around this organizing principle of gauge symmetry.
So the conceptual assumption before quantum field theory was that fundamental forces, electromagnetism, the strong force, the weak force, were just this random collection of interactions.
Yeah, a bunch of ad hoc rules for each one.
But the standard model, which is the most successful physics theory ever devised, is built purely on the demand for mathematical consistency. On gauge symmetry, what exactly is that?
It's the requirement that the mathematical equations describing the quantum fields, the fields that give rise to particles, must look exactly the same. They have to be invariant, even if you locally shift the phase of the field.
Okay, I understand rotational symmetry. If I rotate a sphere, it looks the same. But what does shifting the phase of a field mean in physical terms?
It is abstract, but think of it like this. Imagine you are running a localized monetary system. If you decide to arbitrarily change the value of every dollar bill in this specific room by 10%, that's a gauge shift.
Right.
If the fundamental laws of commerce, buy-sell agreements, are to remain consistent, you have to introduce a compensating interaction. You have to make sure everyone agrees that the 10% shift you just performed doesn't change the outcome of a financial transaction.
And what Cox and Forshaw describe is that the mathematical structure you need to keep the equations invariant under this local phase shift forces the emergence of a compensator field.
Precisely. And the profound structural consequence of this, which was demonstrated by physicists Yang and Mills, is that demanding this symmetry dictates the existence of the force-carrying particles, the bosons, and it defines their exact interactions.
So the interactions that shape our world, why electrons orbit atoms, why nuclei hold together, they aren't arbitrary facts of nature. They're mathematically mandated by this need for abstract consistency.
Yes. If you start with a theory describing electrons that don't interact with anything, a very simple, boring theory, and then you demand local gauge symmetry, the system forces you to add a new particle,
The photon.
the photon, whose only job is to mediate the electromagnetic force to maintain the symmetry. The symmetry itself generates the force.
And this is the principle that allows the standard model to unify the electromagnetic force with the weak nuclear force into a single system.
The electroweak force. And it precisely describes the strong force, which is mediated by gluons, which overcomes the enormous electromagnetic repulsion that would otherwise instantly blow apart the protons in every single atomic nucleus.
The beauty is that the system is self-correcting.
It is. The demand for mathematical elegance leads you, inexorably, to the most accurate physical description of reality we have yet known, covering the interactions of all fundamental particles except gravity.
So if the standard model is so elegant and built on symmetry, where did mass fit in? We know from Einstein that mass is stored energy, but where does the resistance, the inertia, the stuff come from?
Right. The conceptual assumption we had to overcome was the classical view that mass is an intrinsic property, like charge or spin.
But the mathematical structure of gauge symmetry, which we just established, dictates that all fundamental particles must initially be massless.
They must. If you try to write a term for mass directly into the equations, you break the required symmetry and the whole system falls apart.
And that was the crisis of the 1960s. The theory worked perfectly, but it required all particles, including the W and Z bosons, to be massless.
But experiments showed they were incredibly massive.
A huge contradiction.
This impasse was resolved by the Higgs mechanism. It's a set of additional terms added to the standard model's master equation, and it involves introducing a universal, all-pervasive background field.
The Higgs field, which permeates every corner of the cosmos.
Yes. So the physical consequence is that mass is generated through interaction with this field, rather than being an innate property of the particle itself.
This is where the famous analogy comes in, isn't it?
Yes, you can think of the Higgs field as a vast, universal, sticky syrup or molasses that fills all of space.
Okay.
Particles are constantly moving through it. Particles that interact strongly with the Higgs field experience great resistance and therefore acquire a large mass, like the top quark, which is extremely heavy.
And particles that interact only weakly acquire a small mass, like the electron.
That's right.
So what about light, the photon, which is the carrier of electromagnetism?
The photon, crucially, does not interact with the Higgs field at all. It just slips right through the syrup.
And since the photon remains massless,
the mathematical structure forces it to travel at the maximum speed defined by the geometry of space-time, the cosmic speed limit, c laws.
So the Higgs mechanism perfectly solves the conceptual crisis. It allows the force-carrying W and Z particles to gain mass without violating the fundamental gauge symmetry required by the system.
It does. And the discovery of the Higgs boson at the Large Hadron Collider in 2012 wasn't just about finding a new particle. It was confirming the final, essential mechanism of the standard model, explaining the very origin of resistance and inertia in the universe.
Okay, let's explicitly map the entire system that Cox and Forshaw have revealed. Let's define the moving parts and the drivers of the system.
Right. First, we define the actors in the system. These are not just objects, but fundamental entities. We have the particles and fields.
The matter particles, like quarks and leptons, the force-carrying particles.
Photons, gluons, W and Z, and the mediating fields. Critically, including the Higgs field and the electromagnetic and gravity fields.
And then there are the observers and frames. These are the moving reference points that define subjectivity.
Yes. The passenger on the speeding train, the observer on the ground, and those locally flat reference frames. The imaginary, small, freely falling elevators that Einstein used in general relativity to momentarily eliminate gravity and apply special relativity.
Okay. Next, what about the system incentives? What drives the structure toward reality?
I'd say the first is consistency. The internal drive of mathematics is a powerful guide. Maxwell added the displacement current for consistency, and it revealed light. Gauge symmetry mandates interactions for consistency. The physical world is forced to conform to elegant mathematics.
The second incentive would be invariance.
Absolutely. This is the priority of finding universally agreed upon quantities and rejecting subjectivity. The invariant quantities, the space-time distances, the mass and hour, the speed, they must be preserved, even if our everyday measurements of distance and time are relative.
The physical laws must be written using these invariant quantities.
They have to be. And third is predictive accuracy. The system has to hold up under the most extreme scrutiny.
And the predictive success of relativity is just staggering, isn't it?
It's unbelievable. For example, unstable particles called muons, generated high in the atmosphere, should decay before reaching the ground based on their normal lifetime.
But they don't.
They don't. Because they're moving near the speed of light, their internal clocks slow down time dilation, and they reach us perfectly. And the theory predicts the exact lengthening of that muon's lifespan, down to subparts per million accuracy when you accelerate it to 99.4% of $2.
It's incredible. And we also have to acknowledge the competing narratives.
Right. The first is the narrative of common sense. The world is a fixed box of 3 dimensions with absolute time, governed by simple forces where mass is immutable matter.
And the second narrative.
The narrative of mathematical truth. The world is 4-dimensional space-time, governed by non-Euclidean geometry and symmetry, where matter is nebulous and mass is merely a field interaction, and we have to choose the latter, even though it feels fundamentally unnatural.
And finally, the feedback loops that continually confirm this system.
You have theory shaping technology. mc² and relativity are not just academic theories, they're the blueprints for modern technology. Particle accelerators literally stop working if engineers fail to calculate relativistic time dilation and mass increase.
And conversely, technology confirms theory.
High-precision experiments, from the historical Michelson-Morley result to the Large Hadron Collider and the Brookhaven muon experiments today, provide continuous experimental anchors, proving that this counterintuitive mathematical structure is the correct description of reality.
This all leads to the critical lesson that the book emphasizes, the necessity of abandoning intuition.
Richard Feynman put it simply, if a theory disagrees with experiment, it is wrong. Our human intuition is a limited, evolved survival mechanism optimized for navigating a slow-moving gravitational big world. It is a fundamental prejudice that scientists have to ruthlessly discard when pursuing fundamental truths at either high velocity or quantum scale.
So accepting this lack of intuitive comfort is basically the price of admission to understanding modern physics.
It absolutely is.
Yeah. Okay, we've established the complex theoretical structure. Now let's fulfill the promise of the book's title. Why should we care? What are the tangible structural consequences of this deep dive into space-time and symmetry?
I think the most common everyday confirmation of special and general relativity is the Global Positioning System, GPS.
Right.
Without Einstein's picture of malleable space-time, the GPS system would be useless within minutes.
So tell us how that works. Why does time tick differently for a satellite than it does for us on the ground?
Well, there are 2 relativistic effects at play. First, due to the satellite's high velocity, around 14,000 kilometers per hour, special relativity dictates that time runs slightly slower for the satellite than for clocks on Earth.
Okay, so that causes a lag. What's the second factor?
General relativity, which describes gravity as the warping of space-time. The satellites orbit at an altitude where gravity is significantly weaker than it is on the ground.
And weaker gravity means space-time is less warped.
Less warped, and therefore time runs slightly faster for the satellite.
So you have 2 opposing effects. Time runs slower because of velocity, and faster because of weaker gravity. Which one wins?
The general relativity effect, time running faster, is the dominant factor. It causes the satellite clocks to gain about 45 microseconds per day.
And special relativity.
That compensates by about 7 microseconds. So the net gain is about 38 microseconds per day.
38 microseconds sounds minuscule, but if the GPS system didn't continuously apply these relativistic corrections to synchronize the clocks, how far off would the navigation be?
Well, because light travels 300 meters in a single microsecond, that 38 microsecond daily error would translate into navigation errors of roughly 10 kilometers per day.
Wow.
Your GPS would quickly lose all utility. So the fact that the little map on your phone works perfectly is a continuous, high-precision public confirmation of Einstein's theories every second of every day.
Incredible. Okay, next, let's talk about WDSC 2-days as the fundamental engine of the universe stellar fusion.
Right. mc² is not a human invention. It's nature's process. Stars operate by fusing light elements, primarily hydrogen, into heavier ones, like helium.
And when 4 hydrogen nuclei fuse to form 1 helium nucleus, the resulting helium nucleus has slightly less mass than the initial 4 hydrogen nuclei combined.
That's the critical component, the mass loss. That tiny, missing fractional mass has been converted directly into phenomenal energy via em222 soak. The sun is converting about 4 million tons of mass into energy every single second.
And while fusion is incredibly inefficient, only 0.7% of the mass is converted.
The sheer scale of the mass involved, coupled with the gargantuan 2-to-2 exchange rate, provides the energy to keep the sun shining for billions of years. Without the principle of mass-energy equivalence, the sun would not burn. The universe would be dark.
And on Earth, we exploit this in nuclear fission power plants. We aren't fusing. We are splitting heavy elements like uranium-235.
We are exploiting mass destruction. When a neutron splits a uranium-235 nucleus, the resulting fragments, barium, krypton, and more neutrons, have slightly less mass than the original nucleus, and that lost mass converts into energy.
And the efficiency is just phenomenal.
To drive it home, the energy released from burning millions of tons of coal to power a large city for a short time is equivalent to the energy contained in only a single grain of sand's worth of mass if it were fully converted via mc².
So the structural consequence here is that 2-2 is the constant that defines the maximum achievable energy density for any process in the universe.
That's a good way to put it. And our particle accelerators, like the Large Hadron Collider, they routinely confirm the validity of this whole system, showing that mass and energy are interchangeable.
So they operate as ultimate confirmation laboratories for mc². How do they demonstrate mass creation and mass destruction?
Well, for mass destruction, when we smash electrons and their antiparticles, positrons, together they annihilate. The entire rest mass energy of the electron and positron is converted entirely into massless photons light, which carry away all the energy.
The mass is vanished, replaced by pure energy.
Completely. And mass creation is arguably even more spectacular. When we take two particles, say protons, and accelerate them to immense speeds, giving them incredible kinetic energy.
Right.
When they collide, their kinetic energy is so massive that it spontaneously materializes into new massive particles that weren't there before the collision, like W or Z bosons, or the Higgs boson itself.
So the kinetic energy has been converted into rest mass.
Directly. The entire process is a direct test of the conservation of the energy momentum 4 vector.
And the ultimate extension of this entire framework is general relativity, which describes the largest scale structure of the cosmos.
It is. If special relativity taught us that time and space are unified and relative, general relativity, which Einstein finalized in 1915, taught us that gravity is not a force.
It's the geometry of space-time.
It's the geometry of space-time. Mass and energy, which are interchangeable, warp the space-time around them.
So a massive object like the sun is like a bowling ball placed on a stretched rubber sheet. It creates a depression.
Exactly. And an object orbiting the sun like the Earth is simply following the straightest possible path, or geodesic, through that curved landscape. This explains why all objects, regardless of their mass or composition, fall with the same acceleration.
The equivalence principle.
The equivalence principle. The smaller object isn't being pulled by a force, it's being guided by the curved arena itself.
And this curved space-time view is required for modern cosmology.
It predicts everything. From the subtle bending of starlight as it passes massive objects, gravitational lensing, to the existence of black holes and the expansion of the universe, the entire modern picture of the cosmos is structurally dependent on Einstein's revolutionary realization that energy is equivalent to mass, and both define the geometry of spacetime.
Okay, let's bring this back to the core themes of crisis and perception. This deep dive is, it's the ultimate example of how our systems of knowledge operate.
The single clearest link is how human intuition misleads. Our cognitive bias, evolved for survival in a slow, three-dimensional world, creates a powerful prejudice for absolute space and absolute time. But science has shown us that to achieve a deeper understanding of reality, we have to reject what feels comfortable and intuitive. Time dilation, length contraction, the conversion of matter into energy, they are all direct consequences of that rejection.
And it requires this incredible intellectual leap to accept that distance and time are subjective, while a four-dimensional vector length is invariant. So why does abstraction outperform common sense?
Because the universe seems to be built on fundamental mathematical elegance, not human convenience. The drive for consistency and mathematical perfection, whether it's Maxwell being forced to add the displacement current or physicists demanding gauge symmetry, that's what forces us out of the simplistic narrative of common sense and into the most accurate, predictive picture of nature.
The pursuit of abstract, non-intuitive mathematical elegance is what yields technological success.
That's right. And this shows us how invisible systems govern visible outcomes. The most profound realities of our existence, the stability of the atoms that make up our bodies, the reliable light of stars, the origin of mass itself, They aren't governed by forces we can intuitively grasp.
They're governed by invisible, abstract systems.
The non-Euclidean geometry of Minkowski spacetime and the profound symmetries of quantum fields.
And there's a continuous lesson in humility here, isn't there?
There is. The overthrow of the Newtonian system by Einstein was driven by the principle not to extrapolate beyond the evidence. That same principle remains the driving force at the frontier of physics today. It ensures that science is a continuously self-correcting system.
So this deep dive into Cox and Forshaw's work, it really forces a massive shift in how we perceive reality. Let's reflect on what this book helps us see differently.
First, I think, on reality. We have to fundamentally shed the idea that space-time is a fixed, inert arena, a stage for events.
It's an active participant.
It is a dynamic, malleable, four-dimensional entity whose very geometry is influenced by the matter and energy within it. Space and time are, as Minkowski warned, mere shadows of this unified structure, dependent on the observer's motion.
Second, on matter and energy.
We now understand they are not separate substances. They are deeply interconnected parts of the same conserved system, the energy-momentum four-vector. Matter is not immutable, it's nebulous. It's capable of popping into and out of existence, limited only by the immense conversion rate, $2.22, which defines the massive energy potential locked within its rest mass.
And third, on scientific explanation.
Einstein's true genius was not just in solving the problem of light speed, but in taking the simplest, most observable facts seriously, the constancy of $2 and the equivalence principle, and then just logically following the inevitable, relentless, and elegant mathematical consequences.
The most profound discoveries often emerge from taking the simplest of ideas and combining pure thought with ruthless experimental rigor.
That's the method.
And as we conclude, we find ourselves, as a civilization, at a new point of crisis in perception. While relativity is magnificent, Einstein's general relativity, our best theory of the very large, of gravity and cosmology, it can't be successfully meshed with quantum theory, our best theory of the very small.
This is the ultimate current frontier, and it raises this really provocative question. Is space-time itself fundamental?
Does the beautiful four-dimensional structure we've celebrated in this deep dive actually break up or become irrelevant at infinitesimally small distances?
Exactly. Could space-time be merely an emergent property, an illusion that arises from the underlying unknown quantum interactions? This challenge highlights that even Einstein's majestic structures may eventually prove to be merely approximations to an even deeper, yet undiscovered theory of reality.
That potential for a deeper truth is the exhilarating challenge facing fundamental physics today.
Indeed. It forces us to realize that every certainty we hold is provisional.
That concludes our incredibly in-depth deep dive into Brian Cox and Jeff Forshaw's Why Does E is mc², and Why Should We Care?
We highly recommend you seek out this book to delve deeper into the mathematical elegance that dictates our physical reality. It is a truly humbling read.
This project is free and publicly accessible. If you'd like to support the time, tools, and research behind Crisis in Perception, you can become a supporter on Patreon. For a shorter visual overview of this topic, see the mini explainer linked in the description. If you enjoy this kind of systems-level analysis, please like, subscribe, and comment with books or topics you'd like us to explore next.